Let us talk about recursive Java implementation for inserting a value in a binary search tree. So if you take a look at this code, the base case is very clear. If somebody passes an empty tree, then we simply create a new node, and that's the node which is going to represent the new root. We simply return this new root as return value. If the key X that we are inserting, if it is smaller, then it has to go into the left subtree, right? So we recursively call for left subtree. And this is where many people make mistake. They simply write return insert root.left. We need to ensure that whatever this insert returns, it is assigned back to root.left. We'll see with a dry run why do we need to do so. Similarly, if X to be inserted is greater, then it has to go into the right subtree. In this case again, whatever this recursive call returns, we assign it back to the root.right. And at the end, we return root. This root is also returned in the case when you have root.key equal to x, when it is equal to x, right? It would not go in any of these two cases, it will simply return root. What it means is it will not make any change to the tree. Let us do a dry run of this code to understand this part especially. Why are we assigning it back? So we want to insert 20. This is the root that we pass, right? We begin from here. It's not null. So we check whether it is greater or smaller or equal to. So it's greater. This X is greater. So we come to this part. And when we come to this part, we recursively call for root.right. So this becomes our new root. And we begin execution from here. Now root is not null, so we do not go into this part. And root is smaller, so we come to this part again. Or we say X is greater, we come to this part. Now we again recursively call and we begin our execution from this line with this root. We again check for this base case, it's not null. Again we are going into this case and we are going to call for root.right. Now our new root that we are going to pass is null, and we begin execution from here and we create a new node with value X, which is 20. Now if I don't write this line, this 20 would not be connected with 18, right? That's the purpose of this line. So when you call for null, this happens and this returns a reference to this newly allocated node. So this reference returned by this recursive call is assigned back to root.right. This is how they are connected. That's the importance of this line, right? When you insert a new node at the bottom, it is connected back to the parent in the parent call. The control goes back to the parent call and it connects itself with the newly allocated node. Then the control again goes back to the parent call and they simply overwrite the same value. 18 was anyways right of 15 and it again overwrites the same value. 15 was anyways right of 10, it overwrites the same value. And you get your modified BST. Let us now talk about iterative insert in BST. For iterative insert, we are again going to do the search similar to BST recursive insert. We'll decide whether we need to go to the left or right. So while doing so, we'll come here and we'll know that 20 has to be inserted here. The important thing is we need to connect these two. And for that purpose, we need to have reference of this particular node. Now, how do we maintain the reference of parent node where this node has to be inserted? For that purpose, we maintain two references, parent and current. And we stop when current becomes null. So when your current becomes null, your parent is going to have reference to this node, right? And inside this loop, you simply go left, right according to the condition, whether the key to be inserted is greater or smaller. And one interesting thing is, if key becomes equal to any of the nodes, then we simply return root. We do not make any change to the BST. So we have if when current.key is greater, we have else if when current.key is smaller, and then we have else, which means current.key is equal to x. In that case, we simply return the root. We do not make any change to the BST. And before changing current, we keep updating parent as the previous value of current before moving current down to any of its children. Once you come out of this loop, your current is going to be null, but your parent is going to have reference to this node, right? And if parent is null, that's an exceptional corner case. That happens when somebody passes an empty BST to it, when your root passes null. In that case, you will never go inside this loop and your parent will remain null. So in this case, you simply need to return the newly created node. This is to handle the case when somebody passes root equal to null and somebody asks you to insert a key x20. So in this case, what you are going to do, you are going to make a simple BST with this as new root. That's what we are doing here in this part. Now, if we leave this part, this exceptional part, what are we doing here in the if-else condition? We have this parent reference and we decide whether this newly allocated node 20 has to be inserted on the left of this parent or right of this parent. For that, we compare parent.key with x. If it is smaller, then we inserted the left, otherwise we inserted the right. So this line, this particular line connects these two. After they are connected, you return the root. And that's the end of your function. Let us now talk about time complexity of insert. The time complexity analysis is similar to search. If you look at insert, it does search and then some constant extra work for allocating the node and connecting the node. And if you remember search time complexity analysis, the recursive function and the iterative function, they both had big O of h as the time complexity where h is height. Same is the case with insert. Recursive insert and iterative insert, they both have time complexity as big O of h where h is the height of BST. The space, auxiliary space required by iterative and recursive is different. Recursive BST insert is going to need big O of h extra space for recursive calls. Iterative BST insert is going to need big O of 1 extra space. We do not need an array or anything for recursive calls. So it's big O of 1 extra space. That is why space-wise iterative is better. Iterative is also better for one more reason, that iterative does not cause extra function call overhead. But if you see recursive code, it's very tiny code and very simple to write.